Hey everyone. Today we're going to finish off the chapter on oscillations. Maybe a bit short today, but we'll have to see when we get there. To start out, I sort of set up some of the groundwork yesterday. Today I'm going to look at a system we haven't looked too much into, which is a simple pendulum. What is a pendulum? This is just any sort of mass that is free to swing on, a string, or we might say like a massless rod in a homework problem, for example. That's because we just want to consider this mass that is swinging back and forth. So if we have this pendulum and it swings just a little bit. So imagine you have a mass on a string, and you're holding it. It's going to have a natural resting spot. It'll be directly downward. Let me bring the picture up. There we go. It'll have a natural resting spot directly downward. This is the point of lowest potential energy, and it's also not moving at this point. If I just have it very still and I don't disturb it in any way. Let me, so I forgot to do, get one of these colors. Okay. So what if I take that pendulum and I push it just a little bit? It will rock back and forth at some angle. Let me sort of draw out what I'm doing. It'll have some sort of angle of its displacement. And for a good while, it depends on how perfect your pendulum is. I use the word perfect as like there's no rubbing up where you're holding the string, and like the rod itself or the string is close to, if not massless. You don't want that additional mass to be interfering. And we want the swing itself to be fairly small back and forth. If we have this perfect system, it will exhibit some simple harmonic motion. So we have this pendulum. It has a length from its pivot points to where the mass actually sits, L. And it's going to be swinging a specific arc length from here to here of S. What else can we sort of insert on this picture? Well, from the free body diagrams of previous chapters, we could label all the forces involved on this mass. So we have the force due to gravity is constantly pulling downward. Right? F sub G. And we have, we have two different angles. There is the amount, the force that is parallel, or I guess I should say radial to its path. So I'm going to try to like continue this line like that. All right, that's pretty good. we have this radial path that is mg cosine theta, or I guess the sign I'm using is phi, so cosine phi. And we have the tangential components, which is like where this mass is sitting and where it's currently pointing. Let's say it's going that way. So that will be this side right here. So that's mg sine of phi. And since I'm putting that right there, let me put the f sub g right there. So that's the hypotenuse. All right. Now let's do some calculations with this. If we want to, let's say our goal, what we're trying to figure out is how long does it take for a pendulum to swing? If I have something I need, maybe a clock needs to be recalibrated, or maybe I have like I'm making a swing set and I want to figure out some oscillations, like how fast is this, or actually I should say, what does the oscillation depend on? We have this mass here, mass m. We have a length L, and we have some sort of disturbance in its position. So let's say I want to make this thing oscillate faster. What would I have to increase? This is what I'm trying to figure out. Like what is the important bits? What are the important bits of this? So we have this motion, this tangential motion, mg sine theta, and I'll set that equal to sort of the mg sine, I'm going to say theta on accident a lot, so it's mg sine phi times m. This is the second derivative of its arc length right here. And why I'm doing this, it's remember, a second derivative of a position is acceleration. So what this is saying is mass times acceleration, and that is just a force. So ultimately what I'm saying from this equation is that the tangential sort of motion, the tangential motion that way, is due to a force that is pulling it back that way. So those are equal. That's where I'm starting. And since we'll say we have an arc length, the arc length S is equal to L times phi. This is just like radius times angle, position. I'm going to take this, since I know that for a fact. I'm going to take this thing that I just underlined right here. We're going to integrate it twice. And we will get a result of squared s. Integrate twice with respect to time. So d squared s over dt squared. So we have this new expression here. So the length itself, it's not going to change over time as the pendulum swings, the length that the radius doesn't change. So it's only the angle changing with however much the arc length changes. So we're going to take this, or I suppose I'll say we're going to take this and put it in for d squared s over dt squared. Let me for, if you're reading over these notes later, I'll put a star here. So I'll say take this and put into that equation up there. So currently, I'm just saying like there's a force, there's like this restoring force that comes and forces the pendulum back to its original position. And currently right here, I'm finding out how much time that takes. And I can see maybe the length is involved in how long it takes for the pendulum to return back to its original state. So after I do this step, we get d squared phi over dt squared is equal to g over L and also this is where it's somewhat bad design that a couple of chapters ago in angular momentum was also L. This in this case is the length. We've just sort of run out of letters to use. I think there's plenty of other letters. No one seems to agree. So we have this new form. Let's say, there's this sine theta here. Let's say we do consider it's just a small oscillation back and forth. We don't want, large swings because that'll make this calculation more difficult. So I'm just going to say for small angles, and really why I'm doing this is because I just want to get rid of this. And how do I get rid of that? I can just say the sign of it is not there. And what are the conditions for the sign disappearing? It is when the value of the angle is much, much less than 1. So if we have a very, very small angle, the sign of this term is almost non-existent, or it doesn't come into play. So we have the sign of this is pretty much for small angles, the sign value goes away. All right. What's next? We'll say that we know that we know g over L. So that's an acceleration over a length. So that's sort of like the radius. It's one right here, that is an acceleration. And that is this phi right here. That's sort of like the position. What we end up having is, so this is d squared phi. Also, again, kind of poor notation. We were just doing rotation. And this was angular velocity. This is, in this chapter, it's called the natural frequency. I'll get into that in just a minute. So we'll just sort of group that together. Say omega squared phi where omega squared is g over L, and omega is just, the square root of g over L. So this is the natural frequency, or how quickly you think of it. I guess it's in a way similar in this case, since this object does have like a, this object does have like a circular motion to it. This is how frequent, I guess you could say how quick, the pendulum may swing, but it's not necessarily the period of its motion. Period of its motion was t equals 1 over f, or period of motion t equals 2 pi over omega. And since we sort of just solved for this, 2 pi L over G. And I'll say over here for small oscillations. Now, this is pretty much the result we wanted. So what does the period of a pendulum swing depend on? Well, it depends on just, some radial factor. It's 2 pi times the length, square root of the length of the pendulum over gravity. So the only thing is for small oscillations. So as long as this value up here, as long as we keep this small, we only disturb its, like under like 5-10 degrees, very small, and it will oscillate very regularly. That oscillation will only depend on the length of the pendulum itself. So the mass, it could be, I can put like a paper clip at one end and it will oscillate, or I could hang a car off of the same length of pendulum and they will both oscillate at the same frequency, or with the same period of motion. I guess technically the same frequency, since that's omega right there. And I guess for completeness, if you wanted to figure out what's the phi is, let me go like this. I'll say the solution to two stars for that equation is phi naught cosine omega t plus delta. All right. So we've gone from the beginning all the way into how a pendulum gets its natural frequency of oscillation. Think of a person on a swing set. If you are displaced just a little bit, you will have this harmonic motion, simple harmonic motion that will only depend on the length of the swing, or the thing connecting you to the pivot point. But that's not always, you don't always swing forever. If I just, kick off a little bit, I won't just keep swinging forever. You might swing for a long time now that you're at this small angle of, small oscillations. It might continue for a while, but eventually it slows down and stops. Oscillations that slow down have a specific name. Up to this point, I've just sort of said as we have this oscillation and it goes forever. I have this this spring. I have this spring here. Let's see. So this is and I said I disturb it a bit and it goes forever. That's not always the case. We have to look at damped oscillations. These are oscillations that experience some type of force that slows them down, eventually makes them stop. Damped oscillations are pretty much the main type of oscillation we see in the real world. If we're like walking on a bridge and the bridge is sort of, like like a wooden like rope ladder bridge. We walk on it, it doesn't just start oscillating, and then once we leave, it doesn't just keep oscillating, bouncing up and down. It's damped, it's slowed down over time with the friction of the rope and the wood connecting it. It's all dissipated. So there is this force that acts against this motion. Right. Many things do not oscillate when they're disturbed. If I take say I take, again, this is just like a spring, and let's see, what else can I use? Say I take this spring and it has a natural point that it rests, and I stretch it a bit. It will start to oscillate. Eventually it will get damped and slow down. So it's fairly slow now. But a lot of things don't exhibit. You see how it's oscillating for a little bit right here. A lot of things don't even oscillate that much. If I had a like a piece of plastic or a piece of wood. I don't have anything here. I took my phone and I just physically stretched it. I'm going to ruin my phone, but it's not going to, I'm not going to stretch it. It'll be deformed piece of plastic. It'll stretch, but it won't like oscillate. These things that don't oscillate are overly damped or over damped. So they contain the potential to they are still able to oscillate. They're just at this moment they're being forced to not oscillate. That's kind of my point with this. So we have this damping force. That is, I'll just say F sub D is equal to minus B V. V is the velocity of the wave or the oscillation. I guess I could make that omega, but we'll keep it as V. And the B right here, that is a constant. So that's like that's like the degree to which the thing is being damped. So I guess you could say the strength or the modifier. How strong is it? Well, the thing's made out of this type of metal. It's going to have a specific damping constant. We'll say B is constant for each different material. Each different material has a critical damping level. So if things are damped, say I slow this down a bit with some damping, it has a damping constant. There is a critical level, B sub C. Let me write it out first. 2 m mega knots. There is a critical level to where the thing itself that turns it into a gentle oscillation until it stops into something, let me express it like this, into something that just, if I stretch it out, it will just slowly return to its original position. So once it reaches this point, it will then, from there on forward, be overly damped. Which I have, I just didn't underline. The general equation for damped equations, for damped oscillators, for damped oscillator is this differential equation. I'm not going to sort of be testing you on this or anything too crazy. I just want to show that there are many factors that go into this object returning to its original position. So that's all that this oscillation of a spring, of a pendulum, that's all they're trying to do, that you disturb them by some amount of position. So that's position That's a second derivative position. That's one derivative position. You give it some disturbance in its position, and it's just trying to return to its natural state. This is where I bring out the pictures. Okay. So, for example, we had that undamped oscillation. This was in the beginning of the chapter. I said I start oscillating it and it goes forever. There's no damping at all. If we have just a little bit, the object will receive a force that is slowing it down constantly. Say I have a we have this, I guess I'll have to, we have this thing, it's oscillating forever, and I just slowly put my hand on it and I'm slowly forcing it to stop by supplying this constant friction force. The amount of oscillation will decline very slowly. This is damped. And if we have a material that say instead this is a block of clay or rubber or something. I just don't have one in front of me right now. Say this is just some material that if I were to give it a stretch, if I displaced it by some amount, it wouldn't oscillate when I let go. Since I've displaced it some amount, some amplitude, it will then slowly return back to where it originally was and just stay there. No oscillations. That is overly damped. That looks like this graph, or over damped. They're all displaced by some amount of amplitude. The undamped continues on forever at the same amplitude. Let me try to make that look like a... Here we go. Is that, and it's the same on the bottom. Okay. So objects that oscillate have a natural frequency. So if I were to time this thing here, say this is an actual water wave and there's a beach ball right here. Let me try to say there's a beach ball on this water wave. And as the wave, let's see, you got to imagine, I don't have any animation software. If we have this wave itself, this wave is moving. All of these peaks are moving. It's just sort of a continuous wave. And we have this beach ball out on the water. It will constantly be rising up and falling down, and then rising up and falling down. If we were to time this, it would have a natural frequency. This is the frequency it exhibits on its own. This is sort of where I sort of introduce the equations. There are many equations. I'm going to introduce them here. I'll just make like a reference sheet area right here. So we have a natural frequency. And the big general form, this is for any object. Minus, oh, sorry. Okay. That makes sense. Okay, so it's omega 1 minus b over 2m omega naught. If we were to look at a damped system like this, it also has a natural frequency, meaning that the waves, if you were to time when the waves hit you, where you're that beach ball on the waves themselves, you're to time when they come in and pass you, that would remain the same and you'd still have a natural frequency. However, the amplitude, so the frequency is the same, but the amplitude might get smaller and smaller and smaller until you get to 0. So there's this decay time. Which for us right now is just expressed like this. Again, running out of variables, we're going to use tau again. If we wanted to find how much energy is in a oscillating system, it is just, if you start out with a certain amount of energy, the initial energy, times this is the exponential value minus t over t. So if it's just saying, is this a wave that goes forever? If it's a wave that goes forever, there is no decay time. And so the energy sort of blows up. This wave goes forever. This is an infinite wave. Typically, waves in real life are not infinite. We have, a set amount of energy for each wave. And what else? We have, oh, yeah, here we go. We have the Q factor. That's what your book talks about. Q factor. And I'm just going to say underneath, it's how well it is damped. Looks like omega not t. It is tau. Omega naught tau. that. And finally, if I wanted to express the frequency in terms of this Q factor, I can just rewrite that equation at the top. It is omega prime is omega naught like that. Simply just, exchanging variables. Sometimes you're given a Q factor for a specific material. So it's useful to know where to swap things out. All right. There are plenty of other little nuance rules about oscillations. I'm going to get into the next type, though. We looked at something that's damped, something that's an oscillation that is reduced over time. And this is the natural case for most to probably nearly all of the oscillations we see in our daily lives. But there are different types that we can experience. There are damped driven oscillations also. That's a mouthful. Sometimes a damped system will keep oscillating. And so there's imagine this oscillating system. It's not perfect, so it's damped. It's slowing down over time. But maybe it will be forced by either like my hand moving this up and down, or in the case of a pendulum, imagine that pendulum we saw earlier. The pendulum is swinging. It will eventually slow down and stop. It's being damped. The oscillation is slowing down. Would be a force that gets it back up to speed, someone pushing it. So now imagine a swing set out, on a playground somewhere. Someone swinging, and you apply a steady force at a specific instance. So looking at this specific example of the swing set, if we supply a force to an oscillation at a constant interval, so it's not thinking of the swing set example, we're not constantly holding the person and pushing as they go up and then back down. That's not what we do for a swing set. How do we get this amplitude to increase? What we if we're the one pushing, we're standing on one side, and at a regular interval, we give it a push. And it's probably not that big of a push, but we do it regularly. And the person swinging gets a larger and larger amplitude until they don't want to be swinging so high, so you stop them. But this is a really good example of a driven oscillator or a driven oscillation. And the person supplying this force, constantly pushing, just a very little nudge at the right moment. So the person swings up and you give a little push right at the right moment. This is known as resonance. So you are, as the person on the as the person on the ground, pushing the person on the swing set, you have reached the natural frequency. So if a force is delivered at the oscillation's natural frequency, this is known as resonance. And in general, I'll sort of show a little bit of this. Let's go a little bit of the equations. But I want to get to a video at the end of my notes. So it'll maybe demonstrate. So just some external force. Some external force that is some magnitude and is being applied. So that is this, that is being applied at a regular interval. So just a little push here and then a little push there, always at the same constant frequency interval. We take this equation, we sort of, massage it into the equation for damped oscillations. We'll get m t squared d dt over d dx over dt plus m omega naught squared over times x All right, so we have this new form. It's the equation of an oscillator with a force being supplied, a constant force at a regular interval. If we want to find the position of something on a driven oscillator, position for driven oscillator, that is just the amplitude, cosine omega t minus the phase constant. If we needed to know the amplitude, what is the amplitude after a certain amount of time? Okay, so we have that. F naught on the top. So the original force that you supplied, or the force you're applying over this amount of time. And the phase. We have tangent of this phase difference, or this phase constant. M. All right. So let's see. For this supplied force, I think if you want another example, many people have been on a trampoline. And if you're on a trampoline by yourself, you have this natural frequency that you might be able to jump. Sometimes you could jump a little higher. Sometimes you just don't jump with all your effort. But there is this sort of natural rhythm if you were to average it all out. What happens if you get two people on a trampoline? you might both jump at the same frequency, but have you ever tried jumping and someone else is just a little bit off of the rhythm? What happens? One person will end up being sort of forced to jump higher. And this resonant frequency. Someone else is supplying a force that is then making the trampoline push you, or whoever's being the one forced up, able to, forced up way higher than you were naturally going. This is this resonant frequency creating a driven oscillation. So if I was to do just a very simple, I didn't do one beforehand because this drawing gets a little out of hand, but it is just a oscillation that grows over time and can become very destructive. If you're the one being bounced up higher on a trampoline, that can be destructive and getting injured somehow. What other types of systems? So if you match a resonant frequency for someone on a swing, if you push at just the right moment, it is very easy to get someone swinging higher than it would have been normal for you to just do it from a dead stop. So just a little bit of force, added up over a period of time, gets some very destructive results. Let's look at some video examples. So we do have a few of these real examples in person, and it would have been cool to use them, but don't really have that luxury for right now. All right, so here we have, I'm going to keep all of the channel information for the videos up, so I don't own any of these videos. Hopefully you can see that. I think it's going. Yeah, so it's on that and that. I don't want to play the sound. Okay. So we have this driven mechanical oscillator. I'm not going to play the whole video, but there is a motor that is attached to this mass on a spring. So the motor is going to rotate, and this pole is going up, and up at the top there's like a pulley that has a spring attached to this ball and level. Let's go here. Okay. So we have, I want to show that first. So there is this natural frequency that is very constant. And so this rod on the right is showing the phase of the, let me pause. It's showing the phase of this oscillation. It is at a constant rate. And here's the thing that is oscillating with this phase. If we don't have the right frequency, or the frequency is underneath or a little low, the oscillator will just sort of move at a not a growing rate. However, if we have the let's go like this, we have the correct phase the correct push at the correct time, the oscillator will grow to a large oscillation, a large amplitude. And then if we have a phase that is a little too far, imagine the swing set again. If you push the person at the wrong place, if you're not pushing at the back, you're pushing at the base, it's a different sort of force you need to apply. So this case, it's 180 degrees out of phase. They were both opposites, both going in opposite directions on that video. You see, they're out of phase, 180 degrees out of phase. Okay, just in general, let's go to, yes, this one. So now let's go to this example where we have a simulation of, look down at the bottom, there is a mass on a spring and someone can control the drive frequency. There's if you look over here on the left, this little blue block, it's going to be the thing that pushes the spring. And the block on the right, the red one, that is the thing that is oscillating back and forth. So if they have go to where it starts here. So if they have a drive frequency right here, the drive frequency is lower than its natural frequency right here. Its natural frequency is 1.26. So it has a lower drive frequency than its own natural frequency. There is some growth, but then not much else comes of it. It just sort of grows and shrinks, and you'll see this sort of growing and shrinking, very subtle difference. But if this person matches exactly the natural frequency of the mass spring system, so now the drive frequency perfectly matches the frequency of the spring and block. So you're pushing right at the right moment every time. You're giving it the correct push at the correct time. And so you're applying the same amount of force at the same time, but it is creating a larger and larger amplitude. And this can become destructive in some cases. In this case, this graph would just grow forever. So there's that, and I believe what they're going to do, they're going to go above its natural oscillating frequency. So it's not just that you push the thing faster, it will oscillate more. That's not the case. You need to exactly match the frequency of the system. See, it doesn't grow this time. I think the last thing that might demonstrate it is a simulation of, you can think of these as buildings of different height. Since a building has a connection to the ground, that makes it a pivot point right there with a long lever arm. The ground, if it starts to move, say for an earthquake, will then begin to oscillate a building. And it turns out that buildings of a specific length, remember for the pendulum, it depends on the length of an object. depends on how much it will move. So since there's a different length gives a different natural frequency, all three of these, you think of the building heights, have their own unique resonant frequencies. Put that down for me. Okay. What we're sort of demonstrating here is an earthquake. On the bottom, there's this. They're all connected to the same track that is moving back and forth. There are some instances where one building may move and another will not. When you match perfectly that own building's resonant frequency, there will be this driven oscillation. It'll get more and more violent. So the oscillations are just going to keep growing. And here we have a, let's see, it'll show me a bit. Where is it? So here we have, right at exactly 4 hertz, there is a resonant frequency with this tall building. This is something that actually happens with skyscrapers in an earthquake. You need to consider how the building itself will move and flex as the ground below it shakes. And if the earthquake is at a different resonant frequency, say maybe a bit higher, that tall building no longer is violently shaking. We have this middle building right here that is starting to experience something very destructive. You see at any point, like a very rigid, stiff building would just snap in half. I believe they have to push it very fast for the bottom one. Is that, and as they increase slowly, they're increasing the speed of oscillations of the ground below. As they finally reach the resonant frequency of the small building, none of the other 2 buildings are oscillating at the top. Look at the blocks on the top of the other two. They're perfectly still. So this is like a representation of like a upside down pendulum. Depends on the length of the building, gives the building its own resonant frequency. Also, other sort of subtle features too. But we have just 3 examples of driven oscillations and resonant frequencies. Okay, so that is, let me, all right, so that is the chapter. Let me, I just want to do this. So that's the chapter on oscillations. I'm going to start, what is it? Waves. I'll start waves on Monday. And I've made a few changes to the schedule. So the quiz on Monday is not going to be on oscillations. So I'm just sort of, I sort of distribute it a bit differently. So take a look at the schedule that I've changed. I've also taken off the very last chapter from the final exam, because I think that's just packing in a bit too much at the very end. I will also be putting up the the last homework that will cover oscillations, what we just finished, and we'll cover waves. So with this, we have only one more week, and then we are done. So I guess, hold on. So we have 4. No, I have, I'm not going to give a lecture on the final day of class. And I'm only going to give a half a lecture on Monday. So 3.5 more lectures. All right. As always, if you guys have questions, just let me know. Otherwise, I hope you guys have a good rest of your day. And I'll see you later.